Right. Hello and good day, good morning, good afternoon, good evening, good night, wherever you are in the world again, and welcome again to Freaky Physics. Today we are not having a lesson. We kind of have questions from my students from before. And this time around, some students have requested that we go through some uh, concepts regarding the double slit experiment, which is part of waves, and also conservation of quantities in quantum mechanics. For example, charge, lepton and baryon numbers, and strangeness. All right. So that's our topic for today. Oops, in Instagram, I'm still on the wrong camera. All right, there we go. Okay, so there we go on Instagram. So hello again. I'll just adjust that a bit. There you go. Ah, so, of course, since this is basically me just talking about what I know, which is about physics, let's start. Okay, so let's go to the board. Hold on, let me adjust that and uh, change the board for now. There we go. And on Instagram, there we go. Okay, so so let's go to our first topic, which is the double slit experiment. Okay, now in the double slit experiment, I'm not going to go through the details of how it was originally discovered or how it was set up or how it is actually set up. We're just going to go straight to the equation. Okay, hold on, let me get a copy of the equation real quick. uh there we go. The double slit experiment, let's look for a simple version of that. Give me a moment. And also a good diagram from what I can see. This one's gonna work, I think. Single slit, double slit. Is this a double slit? Nope, that's a diffraction grating. Is this double slit? Yes, that's double slit. Okay. Here, let's just go straight and get something from something open source. Okay. Um, yeah, this is gonna work. So Byju's, thank you for this. I'll just copy your image real quick and we'll paste it here. Copy image. Right. Okay, so let's start. Let's actually start. So the double slit experiment. Basically, this is the key idea. Again, thank you, Byju's, for the image. If um you need more accreditation, you let me know. Okay. So anyway, um, this is the double slit experiment. Okay. Now, um, this is the setup. But the thing now is we kind of let's change this setup into something that we would do for IB. Okay. Okay. I think I better change the image. So sorry, by juice again. um. mm, where is okay? I'll just go look for something that the IB would use as the equation. Okay. This time I'm gonna get it from something useful. Hold on. Uh. Nah. Okay. No, that's not the equation. That's not the equation as well. Where's the one with the equation? I think this is gonna work. All right, so I just see that this is from YouTube. I'll credit the source later, but thank you for this source. Okay, copy image. Um, okay, I'll delete that and I'll paste this in. Okay, so for the double slit experiment, let's take a look at how to further understand this. Okay. Um. All right, here we go. So the idea here is for any two slits separated by a distance d, okay? So d would be the slit separation. Small d is the slit separation. So big D is the distance from the slits to the screen. Okay. The next part there, n, that's just these things. N equals 0 for the center fringe. N equals 1 for the first maximum, central maximum, first maximum. N equals 2 for the second maximum or second order maximum, and so on. Okay. Normally we ignore the n. In this case, we normally just do this from 0 to 1. Okay. Normally n equals 1. Okay. And then the last thing we need to do here is the what's this? This, the lambda, which is the wavelength. Okay. S would be this distance here. S is this distance. So there. Okay. Now, I know this is the equation that IB provides, and I know this is also the equation that A level provides. I'm not so sure about the other qualifications. Okay, but the key idea here is that if you rearrange this equation, I want you guys to see this equation and rearrange it. And I'm gonna ignore n for now, so I'm just gonna remove that because that's just equal to 1 in most cases. Okay, so S equals d lambda over d. Okay, now what I'm gonna rearrange this so that the two d's are together like so. So this means this is going to be S over lambda. Okay. Now, I like remembering it this way, especially once you get really familiar with the formula, because it tells you something. Big D is the large separation. Okay. Small d is a small separation. So S here is going to be a small distance. Sorry, a large distance. And then lambda is going to be a small distance. At least with light. Okay. So this is my personal mnemonic on how to remember this. So again, large over small equals large over small. And then this kind of helps it a little bit, right? Because it's both D on both sides. So that's going to be D over D. Okay. And therefore, we're only left with two other quantities, S and lambda. And between the two, S and lambda, the, what's this? The separation distance of fringes versus the wavelength, S is the larger one. So, okay, so that if so once you see the formula, sometimes the formula can confuse you. This is another way to help you remember. Again, do not replace the formula booklet. You're going to be given formula booklets in your qualifications anyway. Whether again it's IB or A level, you're going to begin a formula booklet, but use this to help you remember which letter is which. Okay? So that's the first part. Now, with this in mind, um, all you have to do from here on out is just put the values you have into the formula. Okay, so what do I mean by that? Let's say that you have your let's say that this is your double slit. Okay, and in this case, I'm not gonna draw this to scale. This is your double slit. Let's say that your that your small that your separation distance here, okay, is 1 millimeter. Again, I'm not going to draw this to scale because otherwise it's going to be hard to draw, right? And then let's say that this is your screen. This is the slit. And let's say that the distance between the screen and the slit is 5.0 meters. So you can see that 5 meters is going to be so much bigger compared to 1 millimeter. Um, so this is why this works. This equation works because of this large distance between the slit in the screen as compared to the separation distance between the slits. Okay. Now, okay. So in this case, I'm gonna say that here I'm just gonna note that this is n equals 0, n equals 1, and n equals 2. Okay. And let's give it a distance. So from n equals 0 to n equals 1, let's say that this distance is, let's think of a realistic value. Okay, let's put this at 3.0 cm. Okay. Now, all you have to do before, before that, by the way, before you solve it, make sure you convert all your distances so that you can easily um, do your conversions later on and get the correct answer. So, of course, before you even do anything, I'm just going to write this as 1 times 10 to the minus 3 meters. And then this is the same as saying 3.0 times 10 to the negative 2 meters. You know what? I'll just put this into with 2 sig figs, so 1.0 right there. Okay. So all you have to do now is plug these into the equation. Sorry, this should be big D here, right? So plug these into the equation, and therefore you can solve for the wavelength of the light that would produce this. So what's the wavelength equal to? Basically, you just do this. S over lambda equals big D over small d. We put our values in. Our S again is our separation between fringes or maxima. Okay, so this is going to be 3.0 times 10 to the minus 2 divided by, we don't know the wavelength. That's going to be equal to 5 meters, 5.0 meters over, this is meters, over 1.0 times 10 to the minus 3. Okay, now let's do the math from here. This one's pretty straightforward from here on out. From here, you just do rearrange everything. You'll get the wavelength is equal to 3.0 times 10 to the minus 2 times 1.0 times 10 to the minus 3 divided by 5.0, and then final answer in meters. Okay. Calculating this gives us 0.6 times 10. I chose a really easy value to work with first. It's gonna be 0.6 times 10 to the minus 5. Yeah, 30 divided by 5. Okay, 3 divided by 5 0.6. Okay, so 10 to the minus 5 meters. So that's going to give us 6.0 times 10 to the minus 6 meters. Okay? Or if you want to use prefixes, this is the same as saying 6 micrometers or 6.0 micrometers. All right, so again, that's how you use the equation. That's going to be, again, this is one way for you to remember the formula. Big to small equals big to small. The ratio of big numbers to the small numbers equals the ratio of a big number to another small number. Okay, and then the second number is always d over d, making it easier to remember. Okay, I hope that's clear, and I hope that will find that will make you will find that useful here. Okay, so that's the first bit about the double equation. Okay, now another part here that I would normally see, no, again, no matter what the qualification is, no matter what the exam is, IB, A levels, SAT not so much because it's multiple choice from what I recall. But what else? Well, whatever other qualification you're using. Again, I'm just personally familiar with both IB and A level. Cambridge, yeah, A level. So the idea here now is the next thing we want to go through here is you can think of what happens when you change a value. So what happens when what happens to S? I'll add that. What happens to S when the other values are changed, right? Now, what we can think about here is we can just use the equation, right? When the other values are changed. Okay. Now, one thing you can do here is we'll just do a comparison table here. Now, if you haven't noticed, I love making comparison tables. They make it everything a lot easier to discuss. Okay. So in this case, let's say that this is the quantity. Now we have three other quantities in the equation. We have small d, big D, and finally we have lambda, right? And then the effect on F's. Okay, so remember that the equation, let's just write the equation here. The equation is S equals um, lambda big D over small d, right? So look and see here. Um, let's just say that they all increase, okay? So you can see here on the equation itself, just from the equation first, that when you increase the when you increase small d, which is the slit separation, I'm gonna use pink, okay? Slit separation, okay? The effect is, if you increase this, this should decrease. S decreases, okay? Now, on the other hand, okay, on the other hand, if you increase the either the wavelength or the distance between the slits, so um, distance to screen, this part, and then this is wavelength. Now you can see from the equation that S in both cases will increase, right? Again, the separation distance between fringes will increase, or between maxima will increase. Reason for that is the math. Should be pretty simple if you just follow the math. However, there is a physical way you can remember this as well. Physical consequence, okay? Physical reality, okay? Reality to remember. Okay. Now, think about it this way. Let's start with D, okay? Now, if this, I'm not even gonna draw the double slit for now, okay? Now, remember that the double slit experiment will make the light kind of spread out like that, right? So basically the effect of increasing D is basically you're moving that screen there. And you can see that as the screen moves, what happens? Um, the rays, or not rays, the maxima will move along, that line. Okay, the maxima, quote unquote, move along that line, along this diagonal lines here. Okay, move along the lines. So that's the first one that you can kind of remember. So when you increase D, the maxima, so comparing it here, you can see that the distance between here and here is bigger than between here and there. Okay, so that's the first part, big D. Now, what's the physical consequences of changing small d, the separation distance? The idea here is you don't imagine this moving now. You imagine this, you very far, uh, compare very far slits to a single wide slit. Okay. Now, the reason why we want to do this, again, both of these slits is wide for our mnemonic, or yeah, for our mnemonic. The idea here is this. If you have, and I'm just going to put the slits in as dots like that. Okay. So when you move the slits farther apart, basically what happens is now you have two slits that are very far from each other. But if you move them closer, the eventuality is you'll have your slits actually be one big slit, or one big space. So in this case, again, slits become farther apart, right? And then again, if they're wide enough, if they're small enough, what will happen is more diffraction, which leads to more patterns. But again, we're looking at this with big slits, okay? So in this case, the slits become one. I'll use a different color, okay? Slits become one. Now remember, these are big slits. These are not microscopic slits that will happen to do that diffraction thing that we've been talking about so far with the double slit. Okay? But think about it this way. If you shine your light through these slits, basically the light is gonna come in here, right? And then again, your light's gonna come in here. But if you have your two slits become single slit, you just basically have one big slit, right? So what happened? In this case, you are okay. Uh, let's go back to the equation before we continue. So in the equation, you see here that when you increase the d, you're decreasing the maximum, the distance between the maxima. Again, when you're increasing the small distance d, you're decreasing this. Okay. Now, why is that the case? Or rather, what that might not that case, but how do we remember that? Um, Again, if you can do this from the equation straight away, go ahead, do that. Okay. But the idea here is that for the single slit becoming one, you can think of this as having one central slit, a central maximum. In other words, your n equals 0 is here, and then your first maximum at infinity. Okay? That's one way for you to think about this. Now, of course, this being slits like this, you're going to have a central maximum here as well, right? Central max. Okay? Now, what happens? The farther and farther apart they are, the central max actually, never mind. Let's just keep it like that. So we start from one central maximum here, and then the first maximum is at infinity. So that means the closer you go, closer means first max get closer to central max. Okay. So in fact, never mind this bit. We don't need this. Okay. But this is much easier for me to remember. When the slits become one, you just have one central maximum and then the first max at infinity. Again, with a big slit. It's not with a tiny slit. Okay. Tiny slits, you'll get different results. Okay. So let's just put it here. Um, I'll just rewrite that. So and then from here, so as um slits separate, right? Separate the first max, move in, move in towards central max. Okay. So that is again one way for you to remember what the effect is for putting the slits together. Okay. And of course, going back to the formula again, um, lambda here, right? Lambda is going to be, you increase the lambda, you increase the wavelength, you increase the separation distance. This is again a bit easier to do with a drawing to understand. Yeah. So the effect of the wavelength. So effect of lambda, right? Now, remember that here at the first maximum, so let's say that this is n equals 0 and n equals 1, right? Remember that here, that the path difference is equal to 1 wavelength. Okay, so I'm going to redraw these to make it a bit easier for you to see what's actually happening. So if the first line goes like this, the second line, okay. Oh, sorry, this is going to be the second line. Okay. The top line. Oops, I just tablet just fell. So this is gonna be the line from the second one. Now what's gonna happen here is basically it's gonna be a bit short if this is L, right? If this distance is L, then this distance is L. You can see that it's a little bit short, right? Now that means for this to meet here, in fact, blue is a bad idea. Let's use pink. So you see this little length here? This length here is equal to lambda if this is the first maximum. Okay, so if your path difference is, if your lambda is small or big, now I'm going to redraw this. I'm going to redraw this real quick. Okay. Um, I'm going to try to make this identical in setup. Okay. But this time I'm going to change the wavelength. So if this is the first one here, and then this is the second one here, and it's a bit longer, right? It's going to be a bit longer to get there. And then let's say that this is your wavelength again. Okay. Now you can see here, it's kind of bad if I try to do it here. I'm going to try to do this with a straight line now. See if that works. Okay. So hopefully this works as a better example. Okay. And this time around, I'm going to do this on one set of slits. So I'm going to draw my slits here first. And so just move that. Okay. Okay. So let's draw these as the slits. Okay. Now we're going to draw a straight line first. Let's use first straight line goes somewhat like this. And then the second straight line kind of goes like that. Okay, let's just do it like that. I want to redo it. Oops, sorry. Let's redo that again. There and there. Let's say that that's the first maximum, right? Now, if we actually measure, we don't have to measure that, but I'm gonna draw this like so. Okay, so that's the path difference here. Okay, now I'm gonna draw another line. I'm gonna go back to the line. Hopefully I can make it vertical this time. Oh, cannot do that. Let's try that again. Okay, so as I try, okay, here's a vertical line for our uh screen. Okay, let's try that again one more time. So that's our screen. Try that one more time. I'm trying my best to make that straight. Hold on, one more time. And if I can't, we'll leave it as is. Okay, that seems straight enough, right? Okay, so the next thing we're gonna look at is we're gonna look at another set of lines. This time blue. This, by the way, this will not be accurate to. This will not be accurate to color. I'm just color coding, but I'm not these colors will not necessarily be completely accurate. Okay. Now the path difference here is gonna be a bit smaller. The path difference here would be this only. Okay. Now if you don't believe me, you can actually check it out. You can measure that with a ruler yourself. In fact, I would like to print this out for my next class. Hopefully, if I teach when I teach this later on, I'm gonna print this out and actually see what the path difference is. Well, so the idea here is that this path difference here, this is your delta, this is your wavelength equals the path difference. So delta x, right? So similarly here, your delta x. So let's label that 1 and 2. That will be equal to lambda 1 and lambda 2. Now that means what? From this particular demonstration, we can see that uh, closer S, because remember, that's our S here. Let's say that that's n equals 0. So this would be your S, right? So closer S means smaller wavelength. which is exactly what we have there. Okay, so that's one last thing for you to remember. Well, not remember, one last thing for you to help understand the concept. And then this is actually pretty easy when it comes to the calculation. You already have your formula, put it in the formula, and you're done. Okay, the concept here is this. So let's recap that concept before we move on to the last one. Okay, so again, recapping the concept, what does it mean to S when your other values are changed? When your D here's slit screen or slit separation increases, the effect on the fringe separation or the separation of maxima would be decreasing. But if your screen size, or sorry, screen distance or your wavelength changes, they both increase, S also increases. Again, D, this is the reason why. When you move the screen, the point of intersection between these diagonal lines where you would expect the path to be would vary where you put the screen in. Now big D changes. The easiest way to remember that is when you have a slit, when you have your slits that come together and they become one, you just basically have one central maximum and your first max is at infinity. Okay. Again, in this thing, I want to add that here. Warning, not totally physically accurate. Okay. However, it's a good visual, and that good visual should help you remember which one is which. Okay. All right. And then the last one, effect of lambda, effect of wavelength, bigger wavelength, bigger angle, and bigger angle, bigger slit separation or bigger maxima separation. Okay. All right. So we'll end there. I will not give problems on this. For now, I want to go through the next bit, which is quarks. Sorry, not quarks, which is quantum mechanics, specifically the conservation rules in quantum mechanics. Okay, I think I'll try typing this in. Let's see how to do that. Okay, let's try that. So, in okay, now the one thing I want to go through here before we actually do the problem uh, is how do you know which quantities are conserved, right? So in quantum mechanics, all quantities are conserved except for one. Okay. So just remember that all quantities are conserved. Okay. Lepton number. Now, I want to make sure that this is completely covered because earlier in class when we were talking about this with my students, I wasn't able to cover everything I want to do. Okay. Now, for now, um, mass, we will ignore mass for now. So again, we will ignore mass for now. Okay. Now, in order for us to understand this better, let's kind of do this first. Okay. So charge is conserved. So this means um just count charges. No count charges. There are no special rules for this. Okay. For baryon numbers, one quark has a baryon number of 1/3. Okay. All right. One quark has a baryon number of 1/3. So that means a proton or a neutron would have a baryon number of 1. Okay. Or, all right. Now, lepton number, this is the one that I want to be a bit more complete on. Okay. So the lepton number, there are three types of lepton numbers. We have the electron lepton number. Okay. We have the mu1 lepton number. And then we have the tau lepton number. Okay. Um, okay. So what's this? Basically, the electron lepton number is for the electron and the neutrino and the electron neutrino. So I'm just going to use the symbols. Okay. So again, the electron applies for E and the neutrino. Sorry, not that way. The electron neutrino. Okay. These would be equal to 1. The muon, so this would be, this is labeled Le. Okay. Okay. Now for the mu1 lepton number, this would be for the mu1 and the neutrino, the mu1 neutrino. Okay. In this case, we're gonna use Lm equals 1 in both of these as well. Similarly, for the tau lepton number, this would be for the tau and the tau neutrino. Lt would be equal to 1. Okay. Excuse me. All right. Now, there is one thing we need to know before we continue here. All antimatter particles would have the opposite would have the opposite, or rather would have the negative values of these. Okay. So antimatter all antimatter have the reverse, not reverse, have the negative value of these. Okay, so for example, for the anti-electron or the positron, it would have an electron lepton number of -1. Okay, now of course, if you have lepton numbers, usually in reactions, you just make sure that the lepton numbers or the lepton number is conserved. But in case you see other problems wherein you have electrons, muons, and taus, you have to go into these, the electron lepton number. Okay, now, okay, let's take a look at the very simple formula first, or very simple not chemical, nuclear reaction. Okay, uh, okay, let's go with the simplest possible one that I can think of. The neutron is not really stable. The neutron tends to decay into a proton. Okay. And this thing is the mechanism behind the beta decay. Okay. So knowing that this is beta decay means we must have the electron and the anti-electron neutrino. Okay, let's take a look at why this must be the case. And in order for us to further understand this, I'm going to put this all, again, you guessed it, my favorite solving technique, table. Okay, why? What we're gonna do here is we're gonna do the before and we're gonna do the after. Okay. Now, what do we have here? We'll put here the quantities that we want. We have charge. We have okay, we'll do it strictly by doing the baryon number as is. So baryon number, and then the Le, electron lepton number, the tau lepton number, and finally the what's this? The muon lepton number. So these are the main quantities we're interested in. Okay. So if we look here, the neutron, so I'll just put here neutron. Okay. Now on the after, I'm going to put here the three things. We have the proton, the electron, and the antineutrino. Okay. Let's take a look. Before, the charge is 0, right? Okay. Now, here's the thing though. We're going to assume that we don't have the antineutrino just yet. We're assuming that for now. Okay. So if we look at this, the proton has a charge of plus E and the electron has a charge of minus E, which cancel out 0. So we can say equal to because they're conserved. Let's continue with baryon number. The neutron's baryon number is 1. Okay. The proton's baryon number is also 1. And the electron's baryon number is automatically 0. Why? Because the electron, um, is not a baryon. The electron is a lepton. Hence, its baryon number is 0. Now, if you add these, and we're going to get that. So far, we're okay, right? So plus E minus E gives you 0. 1 plus 0 gives you 1. And those so far match up. So let's take a look at the electron lepton number. At the beginning, 0. Actually, we can say these are all 0 for the neutron. Because the neutron, again, is just sorry, it's not just. It's a baryon. It's not a lepton. So its lepton numbers, all three lepton numbers would be 0. Okay. Now, the shortcut here is you can actually just say L for all the leptons, but it would be safer to do it separately like so. Okay. Now, the proton's lepton number is 0. The electron's lepton number is 0. Now we run into a problem. These would also be 0. So that's equal to, right? So if you think about this, and this is what physicists ran into when they started solving the proton and neutron reaction in terms of the lepton numbers. There's something missing. This cannot happen because that's 0 equals 1. In order for that to happen, there must be, so let's move that a bit. So there must be a third particle produced, right? There must be a third particle. Okay. Now, this third particle, we're going to do it like this. So we're going to call it X for now. Okay. X. Again, we know now that that's the anti-electron neutrino. Now, for this to happen, let's take a look at the conservation again. This means that X, I'm going to use orange for their values, that X must have a charge of 0, a baryon number of 0, and a lepton number of -1. Electron, lepton number. For everything to balance. And then this is also 0, 0. So if you look at here, and we're going to focus on X. So X has no charge and is a lepton. But because it's negative, so X has no charge and is an anti-lepton. So what's the only thing that's an anti-lepton that has no charge? It's the neutrino, specifically the anti-electron neutrino. Okay? And that's one of the proofs behind the reason why we need an anti-electron neutrino in the decay process for the neutron. Okay? So again, this table should help you determine, and you see how I did it? The last particle, I kind of boxed in because this will tell me what its properties are, and therefore it will tell me what the particle should be. Okay, so let's do another one, quick one. What's another common reaction that we could use? Okay, now let me think. Okay, so let's do this particular reaction. Okay, I'm gonna look for a particular reaction first. Hold on, just to make it easier. I don't want to think too hard here. Uh, okay, let's do this example. So we have this particle called the K meson or the kaon. Okay, the kaon, to be specific, the K plus particle is made of an up and anti-strange quark. Up and anti-strange. Okay. Now what happens? This kaon can decay. Okay, I'll definitely check this out. Now this kaon let's say that we are going to draw our Feynman diagrams. In fact, I'm going to get this image from Wikipedia straight away. I think it's easier. Okay. Okay, so Wikipedia, again, thank you for being the free dictionary you are and open source. So hopefully we can do something here. Right. So this is the K. This is a possible, not just the only one, but this is a possible decay mode for the for the kaon. Okay. So what is happening here? Let's take a look first here, one by one. Let's color code this. So looking here at the up quark, you see that the up quark, nothing really happens to it. It stays an up quark, right? Now here, let's put the arrows in. This is an up quark, so that means if we do the Feynman diagram arrows here, they should be pointing to the right if we assume that time goes to the right. Okay, so this means that since this is a strange quark, that means that it must be pointing to the left like so. Okay, now for those who do not remember the rules for Feynman diagrams, the very first rule is once you see a junction with three things coming into it, then the junction must contain an arrow coming out, an arrow coming in, and a non-arrow, um, all incident on that vertex. Okay, so this is our arrow out, right? So that means we have to draw an arrow going in. Okay, and this is our wiggly line. Okay, now the thing here is, does this mean that the up and strange quarks are going backwards in time? Not really. What this means is in terms of the diagram, the antimatter equivalents behave like the matter constituents, as if the matter constituents were moving backwards in time. That's all it means. But it doesn't really mean that the antiparticles are moving backward in time. Okay, so that's the idea. So we have the in going like this, and we have that out going out here. Now let's focus now. So we now have the strange quark here, or anti-strange quark here, and it reacts like so. Okay, let's take a look first at why this is a W plus. Why that's a W plus. So in this case, let's do the table again. We're not gonna do the rest for today. I'm just gonna focus on why that's W plus. So again, this is the in, which is the anti-strange, and then this is the out, which is the anti-up, and then we'll call this for now X, right? Assume unknown. Okay, so if we assume that the W plus for now is unknown, we will call it X, right? So we do the same thing. We do charge. We have baryon number. We have LE. Let's just do LE, LE, L mu, and L tau. Okay, so let's take a look. The strange quark, as we know, is a quark. And my tip for quarks is that if it sounds like a negative trait, not necessarily a bad trait, just a negative trait, it's got a negative charge. So for example, up has a positive connotation to it, it's got a positive charge. Down is negative, so negative. Okay, the strange quark by itself sounds strange, doesn't really sound positive. So the strange quark has a charge of negative, but because this is anti-strange, this is going to be positive, right? And for the positive charges, so this is going to be plus 1/3 E. Okay. Okay, plus 1/3 E. All right. Now for the baryon number, this is going to be 1/3, but because it's an antiparticle, negative, then these would be 0 for the lepton numbers. All three lepton numbers would be 0. Okay. Now on the out, let's take a look at the charge. This is an anti-up. So anti-up would be negative 2/3 E. Okay. So this means for this, we need our X to have a charge of plus 1 E. So let's take a look. 1e minus 2/3 e plus 1/3 e. So they're equal now. Let's go to the baryon number. That's 1/3. This is anti-up. So that's also negative. And then automatic, all quarks, 1/3. This means therefore that the x, and I'm going to put the x in its own little box here. It's going to be 0 for baryon number. Okay. Now, same thing here. Lepton numbers would be 0, 0 here. This means it's going to be 0, 0, 0. Okay. So there are only a few particles that have a charge of 1e, and there's only one particle that would have a baryon and lepton numbers all equal to 0. This means that this has to be a boson. And the only boson that would do this is the W plus. That's why we write here W plus. Okay. So you know the again, the idea here is if okay, I guess we'll end here. But one more thing before we do the X. What if you don't know which particle has what property? It's very simple. Hadrons will have quarks. So all hadrons should have a baryon number. All leptons should have a lepton number, either Le, L mu, or L tau, right? However, if it doesn't have any one of those, it has to be a boson. So again, if baryon number exists, it has to be a boson. Okay? Sorry, not boson. It has to be a baryon. Must be a baryon. Okay? So that's the first part. The second part is if Le, L tau, or L mu exist, not 0, the particle must be a lepton of the corresponding class, of same class. Okay. Now that's the second bit that will help you out, hopefully. The third bit, and this is the last thing I'm going to say for today, is that if neither exist, if B number or Le or lepton number, I'm just going to summarize, I'm just going to just say L. If the lepton numbers are all 0, then this means this has to be a boson. So baryon for baryon numbers existing, leptons for lepton numbers existing, boson if baryon number or lepton numbers are 0. And how many bosons do we know of right now? We have, this could be the photon. So the possibilities are this could be the photon. This could be the gluon. This would be the W plus, W minus, or Z. Could be the graviton. So we haven't proved the graviton just yet. But again, and then the fifth possible one is the Higgs boson. Okay. Now, which of these would you normally see in a reaction? You would normally see either a gluon or a W plus, W minus, or Z. Okay. In IB or A level, you will not see the graviton in equations yet because it's still hypothetical at this moment. And we will not see the Higgs boson because the Higgs boson doesn't really get covered in IB or A level. Okay. The photon, of course, it's covered, but that's a 50-50. Most of the time, you'll get gluons or the W plus, W minus, or Z bosons. Okay. So your task now, if you want to continue this, is to add the arrows and do the same thing here. All right. So hopefully that's all useful to you. And we can end the stream here, I guess. Okay. So with that in mind, everyone, so thank you again for listening. If anyone's listening, thank you for joining us here tonight. Tonight, well, I'm saying tonight because here it's already nighttime, but wherever you are in the world again, don't forget to like, share, and subscribe to the channels. And I will wish you now good afternoon, good evening, good night, good morning, good day, wherever you are in the world, and stay freaky, everyone. Bye bye now.